Thank you, Mr. Chairman, for the presentation. Good evening, everyone, ladies and gentlemen. I'm Luca Vecchiato from the University of Padova, and today I will talk to you about a project we carried out with Professor Meneghetti about a new way to estimate the fatigue limit of welded joints when considering complex geometrical features that are not considered in standards. So the main focus of my presentation will be geometrical details. And if we consider simple geometry about which we know everything in codes and standards, it's so easy to have known the fatigue limit. Problems arise when we have to consider real engineering structures that can be extremely large, huge, have many crack initiation point and location failure, and about which the geometrical feature details is so complex that no one has never provided any structural design curve. So the idea to find a way to estimate the fatigue limit of such structures was going down to the physics of the phenomenon. And as we know from frost analysis and frost experiments, we know that at the fatigue limit, sharp-notched components such as welded joints always exhibit the presence of a crack, but this crack has no more energy to propagate. So the fatigue limit is a crack arrest condition for any notch components made of metallic materials. So since we have a crack, we immediately can think about the fracture mechanics. And the idea of fracture mechanics is related to this so-called, wide-known delta K, the ADN diagram. And in particular, as everyone knows in this room, if the applied stress intensity factor range is higher than a certain value, a threshold value, which is called fatigue crack propagation threshold for long cracks, then we have stable crack propagation until failure. Otherwise, if the applied stress intensity factor range is lower than this threshold value, then we are sure that crack has no more energy to propagate, and somehow we have defined the fatigue limit of our cracked components. The problem is that we have to deal with short cracks since arrested cracks are short, and we all know that short cracks can propagate even if the applied stress intensity factor range is lower than the threshold for long cracks. And this is just because, as we all know, that crack closure phenomena needs crack propagation to develop. So short cracks are more similar to closure-free conditions. And to study the development of crack closure phenomena and the threshold for short cracks, we can use the so-called cyclic curve, which gives us information about which is the fatigue crack propagation threshold as a function of the crack length. And as we see, the initial threshold for short cracks is quite lower than the threshold condition for long cracks, since crack closure phenomena needs time, needs propagation, needs crack wake to develop and gradually build up. So now we have a new instrument, so new information on how to determine the threshold condition, the arrest condition for a crack. But the point is, how can we relate this information with the fatigue limit of such complex structures? And the idea comes from what proposed by Professor Tanaka in 1988, which is called cyclic curve analysis. The idea is that we have our notched components with a crack, then this crack has a certain resistance, the cyclic curve, and the last ingredient of our recipe is the applied loads, is the applied stress intensity factor range, which vary with the crack length itself. And this driving force can be scaled by changing the external load, and we can reduce down the applied external load until we find a tendency condition in between the resistance curve and the driving curve. At this point, the crack has whenever the driving force is equal to the resistance one, the crack has no more energy to propagate, and we have found the arrest conditions. And at the same time, the fatigue limit of such joints, such notch. So this is what we want to do in this presentation. We have 3 ingredients to be mixed together. And the first ingredient is the initial crack size, about which we can spend a lot discussing and arguing about. I've taken some information from the literature. There are many authors that have worked on this topic, especially around the S355 structural steel, which is of interest for this presentation. And let's assume for this work that the 70 microns is a good value for going on. And more information can be found in this review given by Professor Zebt and Mauro Madia. So just trust me, this is not a parameter that's been fit to obtain good results. It's just something we have taken from the literature. The second ingredient was the cyclic curve that has never been defined for welded materials in the literature. So the idea was just performing some experimental test at BAM in Germany by testing some SCMB specimen with a weld. And after test, we obtained the cyclic curve, so the markers in this chart, which has been fitted to obtain our second ingredient, so the cyclic curve, using the famous expression proposed by Meyer-Roper and colleagues in 2014. Oh, sorry about that. Yeah. So the last ingredients we need in our recipe was defining the applied driving force, so the evolution of the stress intensity factor with the crack length itself. And typically the standard approach requires to consider our welded joints, so let's say in this case a longitudinal gasket, for example, and let us consider the weld to failure and perform some finite element simulation that can be quite complex and time consuming just to analyze what is the applied stress intensity factor for a single failure location. And usually for small components, since such analysis can be very time consuming and almost impossible to be carried out on a real huge roller coaster structures. So the idea was just trying to skip all these steps, introducing some simplification, let's say, some hypotheses which are not completely out of the problem. So they can be justified, even if I will not have the time to describe in detail why we have chosen this parameter. And the first idea is, let us consider the weld toe as a sharp V-notch, so with null tip radius, as it's usual in the literature. The second hypothesis we introduce is that let us assume the crack propagates as a planar crack along the bisector line. So we have known the crack path, let's say. And the last information we can add is, let us consider the crack as a through the thickness crack. So just a planar crack through the thickness, which ratio in between the major and the minor axis is equal to infinite. This way, we can just model the problem as a 2D problem, even if this 2D problem is completely representative of many real applications in the case of welded joints. And with this idea, it is possible to move to some observation moved in the literature by many authors that the applied stress intensity factor range of the propagating crack along the bisector line is fixed and known once we have known everything about the stress field in the uncracked geometry, in the uncracked sharp V-notch. And all the information we need to describe the driving force is the so-called notch stress intensity factor, about which Professor Meneghetti gave us a very beautiful insight. And in particular, as you can see from this equation, we have some constants that depend just on only on the opening angle, the crack size, the singularity exponents, and the notch stress intensity factor, which can be used as a scale parameter to find the tendency condition in the cyclic curve analysis. If we do this, we can finally obtain our threshold condition, this time expressed no more in a value of initial, for example, stress intensity factor, but expressed in terms of not stress intensity factor. We have translated somehow a crack arrest condition into a threshold value for the singular stress field had the uncracked component. So we don't have to model anymore the presence of a crack in the weldments. And taking advantage of the peak stress method, about which I will skip any information since we have a good presentation, a perfect presentation from Professor Meneghetti, we can easily calculate a new damage parameter which incorporate information about the notch stress intensity factor. And as we have seen before, the scatter band of the peak stress method was had completely no definition of the fatigue limit, but this time we can enter the value of the notch stress intensity factor at threshold we have found with the crack arrest analysis. So skipping completely the standard fracture mechanics-based calculations. If we do this, we find a fatigue limit at any point at almost 5 million cycles, almost what happens and suggested in Eurocode 3 for this type of failures. And in particular, the threshold value for the equivalent peak stress range, which is our new fatigue damage parameter that does not require any standard fatigue fracture mechanics-based calculations, is almost 170 megapascal. We then finally perform some validation exercise, taking some data from the literature and all relevant to longitudinal assets that exhibit failure at the weld toe. And as you can see, we just need to perform one finite element simulation with the radar cross meshes. So it takes few seconds to run the complete simulation. It is so easy to carry out, and we just need to pick up from the result of the simulation one nodal value of the maximum principal stress at the weld toe. So easy, so immediate to obtain. And if we compare results with the PSM scatter band, we can see that the black markers relevant to broken specimen are completely described and perfectly described in the finite life region. But most importantly, the run-out specimen, the red markers, are completely separated from broken one by the new introduced fatigue limit to the PSM design scatter bands that does not require, again, any fracture mechanics calculations. So moving to the conclusion, I will be quite fast just to leave the time for the questions. We have proposed a new method that does not require to consider any cracking to the structures to apply fracture mechanics and crack closure phenomena to study the fatigue limit of complex structures and complex welded components. We have validated the model using the peak stress method and data from the literature. And again, the cyclic curve has been defined for a welded joints for the first time in the literature. If you are interested about more insight in this work, you can find more details in the presented papers, in the cited papers. And for sure, there are many new ideas we want to develop to extend the formulation we have seen today together. So thank you very much for the attention. I will be eager to answer if you have any question or curiosity.